All right, well, here we are. I guess nobody forgot about daylight savings time, did they? No, that was yesterday. We should all be back to normal or all lined up by now. So here we are. And so what we're going to do is carry on with chapter 8. Now, don't forget the midterm is due tonight at midnight. A lot of you have handed them in, and that's great. You still have time, though. Don't be late. Anyway, so let's get back to it. So let's just quickly go back and revisit what we were doing. And that way we can dive right into the new content, which is a little bit more complicated. Oh, here we go. Yes, go ahead.
I was wondering, because looking at the midterm, I noticed that question 2, at least from what I was getting, wasn't there.
No, question 2 in the midterm?
Yeah, I couldn't
Did I make
see
a
one.
typo in there? All right, let's see.
Possibly. Because question 1 I got, and question 3 through 8 I got. But for question 2, it was the letters, but no questions. It was like computate or whatever it is, like these, and there was nothing to computate.
All right, let me find out. Hopefully there's no typos in there.
Oh no.
Let's see what's going on here. Okay, so somebody has a suggestion.
Yeah,
You
I
did.
don't think I opened it with a PDF.
Well, but you know what? So what was missing?
Yeah, those things. Oh, okay. Oh my goodness. I really thought that
Did you open this up on a Mac?
Yeah, I got no, I have a PC.
Then I'm not sure I understand what happened. Because sometimes what happens is if you go back and forth between a Mac and a PC, sometimes equations and graphs can get messed up. But I don't know. I mean, these are equations from my equation editor, but they're stored here as pictures. So I think they should be visible on either a Mac or a PC. So I'm not sure how to explain what happened. So when you open it up, it was just all blank?
Yeah, just for question 2, though. That's the thing.
Well, those are the only ones that had, so you have a Mac and it worked. Okay. Those are the only ones that have actual equations. The rest of these are just typing, regular typing. That might be why. It would make sense that only these had a problem. Well, do you want me to send you a PDF version of this?
No, I just took a picture. Because I have all the other questions done and I emailed them. But I hope it's all right if I can get the number 2 done and then email that
separately.
Yeah.
Yes,
that's okay.
Yeah, that's okay. Just in the email, remind me that you had to do it separately.
Right. Okay.
Like I'll put them together myself in a folder so that I don't lose one of them. Did anyone else have this problem? Oh, it's starting to look like the answer is no. I don't understand. What kind of computer do you have?
I just have a PC. I mean, is
it like really ancient?
I don't think so.
No.
It seems pretty much like has lights and stuff, so that usually indicates that it's not old.
No, but I mean, it's not like 10 years old or something like that where
there's
no memory in it. And it's a PC, you say, and it just doesn't want to show these equations, huh? Well, I did not expect that to happen. Maybe next time. The reason why I left it as a Word document is I thought you might want to write your answers directly on the document. If you have a PDF, you can't really do that. But, I mean, you could just send me an email when this happens and say, listen, I can't read the equations. And then I can send you a PDF copy.
Cool. Thank you.
But that is kind of weird how that happened.
I guess it's just my luck.
And it's just you, huh? I don't know what that means. There's something. Do you have a virus on your computer?
I certainly hope not.
No. Okay. I can't imagine. So what is it? Just blank is what you're saying?
Yeah. I mean, I see the simplify the following. I see the letters and everything.
Wow.
But I guess just not maybe it's like the little don't know, the radical, I guess. Maybe that's what does it. It's like I can't load that or something, and then just decides not
That's
to.
very odd. I'm going to double check this for a second. I want to see what happens when I double click it. How it reacts to that. Yeah, it's seeing that. See, I have this equation editor here that embeds these in here. And now, if you double click it, you should not get a response if you don't own the equation editor, but you should still be able to see it. So, all right. Well, all right. If you're the only one, I mean, in a way, that's a good thing because there might be something strange about your computer, the way it's been set up. It's not like everybody had the same problem.
Yeah,
but it's not a good thing either. So yeah, I mean, with a PDF, you would have seen no matter what happens with a PDF because it's basically just a picture of it anyway, and so that way you can't have this problem. But you know, maybe next time I'll put both versions up there in case this, you know what I mean? Like you can pick either one.
Yeah.
In fact, you know what I'll do? I'll do that right now. Hold on one second. In case you want to use the PDF. I had no idea this was going to, in fact, well, of course, you know, in the past, I would just hand it out to you in class. So this is only the second semester that I've actually given out. Last spring, we'd already taken the midterm when the virus got started. So last fall would have been the first time that I gave out this exam online, and nobody's had this problem. But you know how crap happens, especially with technology.
Good old technology.
It always lets you down at the worst possible moment. You know that. It always finds a way. You know, it's like I would compare it to having like a pet lion. He might be fun and all, but as soon as his first opportunity presents himself, he's going to eat you. So that's how it works here too. All right, there it is. Now I'm going to open that one up, and maybe you should open it up at home and just see that you should be able to see everything. Okay. Is it working?
Yeah. Okay. It works this way.
You can see everything?
Yeah.
Okay. All right. Well, just chalk it up to weirdness. You know, technology doesn't always behave. I get people send me emails and I never get them. They don't go into my junk box. They just don't go anywhere. It happens. You know, yeah. It always happens when it's important. Not some ridiculous thing, but when it's important, that's when emails are most likely to not appear where they should go. That's how it works. Okay. All right. Well, anyway, that way, now if anyone else runs into the same issue, at least we know that there's a PDF backup in case you need it. And then that should prevent this from happening again.
Thank you.
All right. You're welcome. All right. Let's get back to it. Chapter 8, which was, as we said, it was completely different from what we'd seen before, because now we're looking at interest rates, which are a major part of, which will prove to be a major part of your financial planning during your lifetime. And of course, interest rates influence just about every aspect of our consumer behavior, because these directly determine how much you can earn from saving and how much you'll pay when you borrow. And of course, throughout our lifetimes, we do a lot of borrowing, don't we? Credit cards, student loans, auto loans, mortgages. Borrowing is a regular feature of our lifetimes. And that's what makes it possible to have nice things before we actually have the money to pay for them. Imagine if you had to wait to buy a house until you actually saved up all that money. You I don't know what you would do, but you certainly wouldn't be able to move into your house during your lifetime. But anyway, so what we were looking at here is how interest is actually calculated. And so we'd worked through several examples with simple interest, as it was called. And so simple interest is, if you recall, is interest that's paid on the principal, which is itself nothing but the amount that we've either borrowed or lent. So the word principal, in this context at least, means how much did we borrow or how much did we lend? Okay. Now, the formula, as you recall, is very straightforward. But first, let's reintroduce a few of these variables that we'll be using throughout the chapter. We have P, which stands for principal. And again, this is simply the amount that's either borrowed or lent. R is the rate of interest. And we want to remind ourselves that when we use interest rates in our formulas, we want to convert them into decimals. All right, don't put 5% in your formula. You're not going to get the right answer. If it says 5%, make sure you convert that to a decimal before you do anything else. All right, very good. Now, what else do we introduce here? We had T for time. Now, be aware that this is measured in years. So if you have a fraction like 6 months, you have to convert that into a decimal. Let's say, for example, here, 6 months is half a year. So in our formula, we would write that not as 6, but 0.5, because that represents the number of years. Okay. Now, also a reminder here that the word term means the same thing as time in this particular application. The term refers to how long the loan will last. Now, here's one of the stranger pieces of notation. A is going to be used to represent future value. I don't know why they chose A, but the book decided to go with A. And just be aware, future value simply means if we start out with a fixed amount of money today, this is how much we'll have in the future based on how we invested the money. All right, and this of course depends on the amount we invested. It depends on how much time we invested the money for, and it also depends on the interest rate. And we'll of course be using these formulas throughout the chapter. Now finally, we have another interest reappears here in a slightly different form down here with this I. This is the dollar amount that we earn, not the percentage, but the dollar amount. So how much interest do we actually earn? How much money did we put in our pockets? That's what this I represents, a dollar amount, as opposed to a percentage. All right, so with all that being said, we're very well prepared for what's coming. We started out by calculating simple interest with a very basic formula. And of course, we like basic formulas because they're easy to understand. But you'll see later on today that it has limited applicability, and that eventually we'll have to replace it with something more sophisticated. So we start out by noting that the simple interest is the product of 3 terms: the principal that we borrowed, the rate of interest that we are being charged for that loan, and the time over which we have borrowed the money. And of course, this also applies to putting your money in the bank as well. So in other words, how much money did you start with? How much is the bank paying you? And how much time is involved? All of those will give us the amount of simple interest that we're earning. Now, obviously, this is good to know. I mean, sure, you throw your money in the bank, and at the end of the year, you can look at your bank account and see how much you have. But it's very helpful for financial planning purposes to know in advance how much you'll have at the end of the year. Suppose, for example, you're trying to save to buy a car. Well, it helps your planning a lot if you know how much your investments will be worth in the future. So if you decided, oh, I think I would like to buy a new car, I want to save up enough money for the down payment, which would be, let's say, $3,000. It's very important to know how much the money you put in the bank will be worth in the future when you go to buy that car. And this way you can figure it out and not be, let's say, surprised when you get to the end of this time frame and you don't have enough money. Okay, this way you know exactly how much you'll have. Anyway, so we have a couple of simple examples here. We started out by noting that if an investor deposits $1,000 for 1 year in a bank account that pays a rate of 3% per year, then we can plug those numbers into this formula. And again, you note that here that this 3% was converted into 0.03. We didn't just leave it like as 3 in the formula. So we plug in all the numbers and we end up with $30, which is the product of 1,000 times 0.03 times 1. And by the way, there's an important detail right here too. I just want to point out, notice how it says 3% per year. Interest rates, I'm writing this in red because it's important. Interest rates are always quoted on an annual basis. So in other words, when you hear the 3%, you know it means 3% per year. You don't have to ask. It means 3% per year. Now, in our formulas, we can adjust this for different time frames, but 3% is understood to mean 3% per year. All right, so just when you hear those words like 3% or 5%, it always means per year. All right, now what we also did with this information is we calculated the future value of this investment. In other words, we know that we earn $30 in simple interest. How much do we have in our bank account and when the year is over? Well, for that, we have to include both the interest and the principal that we started out with. So in other words, yeah, we can't just ignore that. The interest is $30, but we actually have in our account more than that. In fact, we end up with $1,030. Now, how do you know that? Because we started with $1,000, the bank gives us $30 worth of interest. At the end of the year, our total balance is $1,030. And also, I just want to point out here that the terminology that we're using in this chapter is that the future value of $1,000 is $1,030. Okay, so in other words, future value can be thought of as how much do we have in our account at the end of the year. That would be the future value of our initial investment of $1,000. So when you hear the words future value, it just simply means how much will we have in the future. All right, and that's where the name comes from. How much will we have in the future? In this case, that would be $1,030, which consists of the initial investment of $1,000 plus the interest. Now, we can do this more quickly and more directly by using one of these two formulas, which both actually mean the same thing. So the first one just says, listen, if you want to know the future value, well, you're just going to take your principal and add your interest, and that's it. When the year is over, that's how much, or actually it doesn't have to be a year, it could be any time frame. When that time frame is over, the amount you have in the bank will come from this formula. That's your future value. But algebraically, you recall that I has been defined as being equal to PRT, which means that I can now turn this into a slightly different version by replacing I with this PRT over here. And so by combining these, it turns out this is the same thing as this. Okay, so they both mean the same thing. So you should use the one that makes the most sense given the information that you have. All right. Now, with all that being said, we saw that we can take that formula and we can rearrange it algebraically to solve for other terms in that formula. But before we do that, I just want to remind you, well, first let's look at the numbers here. Let's just run through this problem one more time where I show you how each formula gives us the same final result of 1,030. For example, using this approach, the future value you can see is simply the principal plus the interest, which adds up to 1,030. But we'd also like to confirm that the other version of this formula works as well. Okay. So I'll give you a minute to catch up and then we'll see how that works. All right, so if we use the other approach, then we would have done it this way, okay? So in other words, you know that the interest rate is 3% per year, which is converted to 0.03. T is 1 year, and of course the principal is 1,000. So in this case, what you're actually doing is multiplying 1,000 by 1.03 to come up with this result. Okay. So of course, obviously you can see that either way, we got the same result. All right, now, as I started to allude to, we saw once before that we can take the same formula and apply it to fractional parts of a year. And let's say, for example, we have a situation where an investor deposits, let's get these lines out of the way. An investor deposits $1,000, but for only 6 months in a bank that pays 4% per year. So the only thing we have to watch out for here is that T is not 6, like I said before. It's 6 out of 12 years or 0.5 years, half a year. 6 months is half a year. So when you look at this formula, I equals PRT, you can see that 1,000 is the principal, of course. 0.04 is the annual rate of interest. But because it's only a 6-month investment, we have to put in T equal to 1/2. And so you can see that when the 6 months are up, that means we got $20 worth of interest. If we'd left the money there all year, we would have had 40, but sadly enough, we didn't do that. So we only have 20. That's our simple interest. And again, I've mentioned down here in the bottom, the interest rate is expressed on an annual basis. And so therefore, that's why this adjustment is necessary to have T be equal to a half a year. So that, in other words, it's 4% per year, but 2% for 6 months. Beautiful. All right, so that was pretty straightforward. Now, on the other hand, what if I put the money in there for more than a year? What do I do then? Well, let's look at the opposite case where the time frame is more than a year, and you'll see that it's very simple. Okay, how simple is it? Well, what happens in this case is instead of the money being left in the bank for 6 months, I'm going to leave it there for 2 years. So now, again, 4% is the annual interest, but we leave it there for 2 years. And so you notice how I've used both of these two versions of the formula. In both cases, I wind up with 1,080 in the bank, of which $80 is my simple interest. So it's, like I said before, it's $40 per year, which implies $80 over a span of 2 years. All right. Now we can see how to calculate other variables from this formula. Okay, so you might remember that we can take as our starting point our simple interest formula and rearrange it algebraically to solve for the other 3 variables, by which I mean principal, interest rate, and time. And in, depending on what problem you're confronting, you might need to do any of those 3 things. So how would you do that? All right, let's see. I'll just give you a minute to catch up. And then we'll investigate these other alternative versions of that formula that let us calculate the individual components. Okay. All right, I'd say we're just about ready. right, here we go. So let's start out by solving for P. Okay, so if we wanted to solve for P, the principal, here's what we would have to do. So remember, this is our starting point. This is the original equation. And algebraically, to solve for P, I just need to divide both sides by RT, and this is my final result. Now, how do you know when to apply this formula? If the question gives you the simple interest, the rate of interest, and the time, and they ask you to figure out how much this person has saved or invested or possibly borrowed, then that means you're being asked to calculate the principal. So you should be able to tell from the problem what information they've given you and what they're asking you to do, whether or not that is what we're doing here. In other words, if they ask you how much a person has borrowed or lent, then they're asking you for the principal. Like this case, where a homeowner has borrowed from a bank to finance repairs, which happens all the time if you own a house, as you know, and this person ended up paying $20,000 in simple interest. Let's say the rate is 4%, and the money was borrowed for 5 years. How much must this homeowner have borrowed if he ends up paying $20,000 in simple interest? So this is an opportunity to use this formula, P equals I over RT. The only thing we got to watch out for is the parentheses in our calculations. What do I mean by that? All right, let's find out. So this is the actual algebraic formula, but if you're going to do this on your calculator, you've got 20,000 down here divided by, you must put the entire denominator in parentheses. Okay, without the parentheses, you cannot get the right answer. So don't forget about that. So in a case like this, you've got 20,000 divided by the product of 0.04 and 5, and that will give you your final answer of $100,000. So the homeowner borrowed $100,000 for 5 years at a rate of 4%. And as a result, ends up paying $20,000 in simple interest. All right. So now what we're going to do next is solve for the rate of interest. And again, it's just a simple matter of rearranging our simple interest formula to come up with the result we need. Okay, so algebraically, this is not that big of a deal. It's pretty straightforward. All right, so let's find out how we would solve for the rate. So we start with the original equation again, and now this time we're dividing out by P and T to come up with I over PT. That's how we'll solve for the rate of interest. And again, remember, this is a percentage. So, but in the formula, it'll be a decimal. All right, so we should be able to figure out how to interpret that. All right, let's see how that works. So, whoops. So suppose an investor puts $1 million into a CD. Now remember, a CD is a special type of bank account where you must leave the money there for a fixed length of time in order to earn a higher rate of interest. So let's say that we decide to buy a one-year CD for $1 million, and we're told that when the year's over, we'll have earned $20,000 worth of simple interest. It's only 1 year, so T is 1. That means we should be able to figure out what rate of interest this bank is paying, because we know the special formula R equals I over PT. Okay, so when you plug in those numbers on your calculator and you do it correctly, you should get the right result. So then you see you've got 20,000 over a million times 1. And so, and again, down here, you note on the calculator, you've got $20,000 divided by parentheses, $1 million times 1 equals, and then you get 0.02, which you interpret as 2%, because 0.02 times 100 is 2%. All right, so that's that one. Okay, now the last one that we still haven't considered is the time. We can also solve for the time of a loan or an investment by, again, rearranging the formula and solving for t. All right, let's do that. So again, you start with the original simple interest formula. And this time we're going to divide out both sides by PR. And this is our final result. That's how we calculate the time, which again will be measured in years. All right, let's look at this example. An investor puts $100,000 into a CD, again, CD, which means you have to leave it there a certain length of time, that pays an annual rate of 3%. And we're told that the investor will earn $30,000 in simple interest. What we don't know is how long the money has to stay in this account. Okay, in other words, how long will it be until the CD matures? And all of that tells me that we're solving for T. How long will it take to earn $30,000 worth of interest in an account like this? So now you know what that means. That means it's time to whip out this equation that we just determined. T equals I over PR. Okay. So then we plug in the numbers, carefully applying them to our calculator. And don't forget about the parentheses, because if you do, you're not going to get the right answer. But when you plug in all those numbers, you should be able to get a total of 10 years. So in other words, it took 10 years to earn this interest when we deposited $100,000 in a CD that pays 3%. Beautiful. Okay, so if you did everything correctly, you should get the same numbers. Now, we're ready for a very advanced topic here. I did mention earlier that there's two basic kinds of interest you could possibly earn or pay. And the one that we've been studying up to this point has been what we call simple interest. But in addition to that, there's another kind of interest you may encounter, and it is referred to as compound interest. Okay, now this is where it gets a little bit more complicated. Because what's happening here is that all of a sudden, instead of just earning interest on principal, we're starting to earn interest on interest that we've previously accumulated in our account. Or in the case of a loan, you're paying interest on previously, the interest that you previously paid. So what's happening now is that there's a second source of interest that you can earn from a bank account under certain conditions, that is. So there's really then the two types of interest that we can earn from an account. Let's say we put our money in a CD at the end of, let's say, 10 years. There's actually going to be two sources of interest. The one that we've already studied intensively, which is the simple interest. But in addition to that, you may also earn something called compound interest. It turns out, though, that in the early years of an investment, the compound interest is likely to be very, very small compared to the simple interest. But the longer you leave your money in the account, the more and more interest is compound interest, and the less is simple interest. So the amount of return that you're getting will be mostly simple interest, but if you leave the money there long enough, eventually you'll also have a significant amount of compound interest. All right, so all of these investments that we're making will give us potentially two sources of interest then. And again, we'll summarize it here. Interest on principal, which is our familiar simple interest, and interest on interest, which is known as compound interest. The challenge is calculating compound interest. It's a more complicated concept. In fact, so much so that I decided to take a step sideways and introduce it with a very important example before we look at the actual formula, which is pretty scary when you see it. And so in order to minimize the scariness, I want to show you exactly where it's coming from. All right, once you understand it, you will not find it scary at all. But if I just show it to you, you'll be scared, believe me. Okay, so why don't we sort of step aside and take a look at an example where an investor puts $1,000 into a bank account for a year that pays 4%. Well, fine, we've done this before, and you can see using our simple interest formula, we should have $40 worth of simple interest at the end of the year, and our balance, of course, at the end of the year you can solve it once again as A plus I equals 1,000 plus 40 equals 1040, or P, wait a minute, what did I do? Sorry, this is P plus I. Hold on one second. There we go, that's better. Okay, so we have simple interest of 40, which implies that our future value must be 1,040 because we're just basically adding on our original principal. Now, in order to illustrate how this works, we're going to introduce a very special type of graph, which is called a timeline. And timelines are heavily used to help us understand cash flows that take place from an investment. So we're going to use that right now to show exactly what just happened. All right, and when you see this diagram, you might say, well, that's kind of interesting because it helps us keep track of the flows of cash throughout the lifetime of this investment. So how does this thing work? All right, let's find out. So the way it works is time evolves from left to right. 0 means today. 1 means 1 year in the future. Actually, let me add a little something to here. Let's call that T. T equals 0 means today. T equals 1 is 1 year in the future. Now, you notice what I've done here. Today we have the principal. It's $1,000. What do we have at the end of the year? We have our future value, which we've just seen from our formula is $1,040. So there's nothing really new here. It's just a way of visualizing what's happening with our investment. Now, we're going to complicate things a bit here. Up to this point, we've been assuming that when a bank pays you interest, they wait till the end of the year to pay you the full amount. What if it doesn't work that way? Suppose this bank says to us one day, you know what, we've changed our policy on interest payments. Instead of giving you 4% at the end of the year, we're going to do this. We're going to give you half of it in 6 months and the other half at the end of the year. In other words, 2% halfway through the year in 6 months, and then the rest at the end of the year. Now, this will be a good opportunity, I think, to take a poll. Not that you have any way of, well, all right, let's try this. I just want to try a poll here. And just to give you an idea to think about what we're doing here. So will we have a larger balance in our account at the end of the year if interest is paid twice a year instead of once per year? So in other words, we could, before we were getting 4% at the end of the year, now the bank is saying, listen, we're going to pay you 2% twice a year. The question is whether or not this is going to help us. All right, here we go.
This is assuming that it's the same percentage each time,
Yes,
right?
that's right. So right. In other
We're
words,
just double checking.
Right, 4% once a year compared with 2% twice a year. All right, and a lot of people are like, I don't know. Well, that's all right. So the answer, as we'll see in a couple of minutes, is yes. This is actually good news to us as the savers, because we'll actually wind up with more interest than if the bank paid us once a year. Now, of course, the drawback here is that if we are the borrower, it's going to cost us more interest. So this is only good news for savers. It's bad news for borrowers. But we're going to see how and why this is happening, all right, in the next slide. So here's what we're going to do. We're going to go back to our diagram, and this time we're going to complicate it a little. We're going to have two different cash flows here. So what's going on here? We start out with our $1,000, and in 6 months, I apply my future value formula, 1,000 times 1 plus 4%. Now, if you notice, this is 6 months, so T is only 0.5. And that means at the end of 6 months, I'll have $1,020 in this account. And we've already seen an example just like this one. Okay, so let's get that straight. Now, this part, there's nothing mysterious about this. 6 months from now, we'll have $1,020. But this is where it gets interesting. In 6 more months, we're going to apply the same formula. But this time, the principal will be 1,020 instead of 1,000. Because now we have not only $1,000 worth of principal, we have this extra $20 in interest. So then we apply the same, the rest of the formula is the same. 1 plus 4% times 0.5. That 0.5 is there because this is 6 months later. And when you multiply that in your calculator, you'll notice something very interesting. Look at that number. It's not 1040 like it was before. There's all of a sudden this extra 40 cents. Where did that come from? Oh, well, that 40 cents is based on the fact that during the second half of the year, we earned interest not just in the original principal of 1,000, but this $20 worth of interest that we got during the first 6 months. So this 40 cents is what we mean by compound interest, which is the same thing as saying interest on interest. Is that, so you can see what we're talking about here. By changing the interest to twice a year, even though it's still 4%, all of a sudden we've got this extra 40 cents in our account, which is compound interest. Are we happy about this? Yes. Yes, it's only 40 cents, but you know what? It's still our money, isn't it? Anytime somebody offers to give you more money, you always say yes, don't you? What do you, you can imagine yourself going to the bank at the end of the year and they say, your balance is $1,040.40. And you say, oh, that's all right. You just keep the 40 cents extra. I don't need it. Is that ever going to happen? No, because that's your money and you've earned it. So even though, like I said earlier, the compound interest is likely to be very small for when we have short-term investments like this. But if we kept the money in the bank, not for a year, but for 20 years, the compound interest would grow very, very quickly. And in fact, eventually, there'll be more compound interest than simple interest, but that takes a long time. Right now, we just want to focus our attention on how this is happening. Why do we have more money now than we did before? It's because, again, we earn interest on this $20 worth of interest. Right there. That's where the extra amount is coming from. The interest is being applied to both our principal and this extra interest from the first 6 months. All right, now, just to see, let's take this one step further and let's try a situation where instead of 4% once a year or 2% twice a year, let's try the case of 1% 4 times a year. Okay, that's right. You can watch the video if necessary. All right, now I'm going to do another poll. Interest rates. 2. If we now pay 1% 4 times per year, will the balance in our account increase above 1040? In other words, if we change it to 1% 4 times a year, will the account balance go up even further above $1,040.40? All right, let's find out what we think. All right, so, well, people are still voting, okay. All right, well, the answer is yes. Okay, just the short answer is yes. Every time we increase the frequency of the interest payments, the balance in the account will grow even faster. So we're going to prove it right now by doing this with well, we're going to pay not 4% once a year or 2% twice a year. We're going to go to 1% 4 times a year. Now, there's a lot of calculations here, but you'll see at the end that in fact, this increases our balance even further. Okay, so let's do this. Now, this is going to take a little while. So I hope you'll be able to follow through all the steps and see what's different now. All right, so you can see I've got 4 points during the year when I'm going to earn interest. In 3 months, or 0.25 years. In 6 months, or half a year. In 9 months, or 0.75 years. And in 1 year. Each time we apply the same formula, it's still 4%, but now it's a quarter of a year each time. So basically, each time I earn more interest, I'm multiplying the balance of my account by 1.01. So after 3 months, my $1,000 grows to 1,010. Here's where it gets interesting. What about after 6 months? What's changed is that the principal in this for 6 months is not 1,000, it's 1,010 because there's $10 worth of interest from the first 3 months. So therefore, at the end of 6 months, the balance in my account is now $1,020.10. Now remember, in the last example, after 6 months, we only had $1,020. So already the interest is increasing. Now we move down to 9 months. And again, look what happened. The principal is whatever we had at the end of 6 months, which is 1,020.10. So after 9 months, our account balance is 1,030.301. Ooh, as you can see, it's growing pretty quickly. And then finally, this 1,030.301 is our principal in the fourth calculation. And guess what? Now you apply this 1.01 to it, and we end up at the end of the year with $1,040.60.4, which is, remember the previous example, we only had 40 cents. Now we have 60.4% cents, which means that yes, it's not a huge amount of money, but it did go up. All right. So it did. We were, everyone who said yes in that poll was correct. The amount in our account at the end of the year went up even further because the frequency of the interest payments went up from 2 to 4 per year. Man. Now you can see this is a very time-consuming process. Very time-consuming. What if I'd said 8 times a year or 12 times a year? We could have been here all day. These two examples were just here to illustrate what compound interest is all about. In a few minutes, we're going to be introduced to a formula that can take care of all of this for us with one simple calculation. All right, so don't worry, you won't have to do like whole streaks of these formulas. Instead, we're going to have a single formula, which is a little messier, but it will do it all in one shot. Wow, that should be cause for celebration. Like I said, this would be very complicated or very time consuming if we had even 8 periods per year. But that won't be necessary. All right, now the main thing is I hope everybody really understands why this is different than what we had earlier, because now by breaking it up into pieces like this, each period we get interest on our principal and our previously earned interest. That's why it's growing faster than it did when we only earned interest once a year. All right, I'll give you a minute to catch up. Now, what I've done here is in the slides, I've summarized these results into a single chart so we can look at it all together at one time and hopefully understand precisely what's going on here. All right, the calculations are important, but we want to understand what they're telling us. All right, so I'll give you another minute or so to catch up with all these complicated calculations, and then we're going to look at a chart for a minute and see what this means, and then we're going to do some more advanced examples based on this amazing new formula, that the one I mentioned earlier, that if I'd showed it to you right in the beginning, it would have been extremely scary. Now when we look at it, you'll see that it's not all that scary. All right, are we caught up? Very nice. So what I've done is I put together a little chart that helps us visualize the relationship between these numbers. So let's take a look at it. Okay, so I obviously wrote this by hand. So what I've done is I've got in the first column the frequency of which the interest is paid. We had 3 cases, remember, once a year, twice a year, and 4 times a year. We calculated the future value in each case, and you can see we started at 1,040, then we went up to $1,040.40, and then we had $1,040.60.4. Now, the total interest in the next column is equal to the future value minus the principal. Okay, so in other words, because we started with $1,000, this future value, 1,000 is principal, the rest has to be interest. So you notice in each case, all I've done is subtracted $1,000 to get to this column. Now, also, based on our simple interest formula from up here, $40 is the amount of simple interest that we will earn from this account. I put that in this column so you can see that of the total interest, initially, when we only have interest paid once a year, there is no compound interest. But when we do this twice a year, that extra 40 cents is what we call compound interest. And then finally, when we have interest paid 4 times a year, the compound interest is 60.4 cents. So that tells us something. That's the important detail. The more often interest is paid, the higher will be the compound interest. And we're going to see that, of course, in a few minutes. We're going to do some examples to show or confirm that this is actually true. All right, so the more often we get paid interest, the higher will be the compound interest. But the simple interest never changes. In fact, you can kind of tell by looking at the formula. There's no mention in this formula of compounding or frequency of interest, so that it stands to reason that that will be the same regardless of how often the interest is paid. All right, so I'll give you a minute to catch up, and then I'll show you one more important detail before we dive into that scary new formula. All right. Now, as far as the terminology goes, I do want to mention that the number of times a year that interest is paid is referred to as compounding frequency. All right, so I've made a little chart here so you can keep track of it. If we get interest paid once a year, we call that annual compounding. Twice a year, we'll call that semi-annual compounding. 4 times a year will be known as quarterly compounding. 12 times a year will be known as monthly compounding. And 365 times per year will be known as daily compounding. So it makes perfect sense. All right. So when you hear these terms, compounding frequency, it just tells me how many times a year I will get paid my interest. Now, I'm going to do another fun poll, just because I'm curious to know if you've ever been exposed to this or not. Let me make sure you can still see what you're doing here. Oh, no. All right. I'll put that slide back up in a second. Hold on. So for banks in the U.S., what is the normal compounding frequency? All right, so we're going to have annual, semi-annual, quarterly, monthly, and daily. All right. So we'll hang on to this for a minute until everyone's caught up. All right. And then we'll fire away at this poll. But so again, these are the ones in practice you don't normally see any other frequencies. In other words, you're never going to see, for example, 9 times a year or 17 times a year. These are the standards, but there's certain ones that we see most frequently. All right, it depending on what kind of investment you're making. The compounding frequency typically falls into one of these categories, and you can see why, because they make perfect sense. But just out of sheer curiosity, I'm going to poll you on this. So in other words, if you put your money in a US bank, what kind of compounding frequency do you expect them to offer you? All right, I think we're just about done. Well, the funny thing is, obviously, if you don't know, you don't know. I mean, I'm sure a lot of you are guessing, but it turns out that banks in the United States, at least for savings and checking accounts, are offering you interest compounded daily. Every day you are credited with interest in your account. If you can believe that, it seems hard to imagine. Why would they do that? Because they're actually paying you more interest. But don't worry, they make up for it by doing the same thing with the borrowers. So when you go in the door and say, I need to buy a car, they're also going to charge you interest on a daily compounded basis. So it's normal practice in the US for interest to be compounded on a daily basis. And so that helps you if you're saving your money, but it also works against you if you're borrowing. All right. Anyway, so why don't we jump ahead now? And here it is. I just want to remind you one more time. When the compounding frequency increases, the future value of your account goes up, the total interest that you're earning goes up, the compound interest goes up, but the simple interest never changes. So it helps you if you're, like I said, if you're the lender, you're saving your money. But if you're a borrower, this means that your cost will be even higher. So, when you get it, if you have a credit card, for example, well, we'll discuss that later on in the chapter, but you'll notice that the same thing is happening. They're charging you interest on a daily basis. All right. Now, what I'm going to do is show you that scary formula I alluded to earlier. But before we do that, I need to introduce one more variable. And that will help us. And once this is done, the formula that I'm going to show you, only consists of terms that we've already seen before. So we're going to introduce the variable n to represent compounding frequency. So in other words, if the problem tells you that interest is compounded annually, you'll set n equal to 1. For semi-annual, n equals 2. All right. Actually, you know, it just suddenly dawned on me. Hold on one second. I think there's a way that I can show 2 slides at once. Oh, okay, it doesn't look that great. All right, never mind. Because what I'd like you to do is see them all together in one place. But so yes, you can see where this is going. Annual is once a year, n is 1. Semi-annual is twice a year, which is n equals 2. And what about the other cases? You know what? Why don't we try this? Why don't I sneak these all into the same slide? I bet I could do it if I'm careful. I really would like to have all these together in one place, ideally. There, it just barely fits, but it does. All right, there we go. So now it's a beautiful slide. Oh, whoops. All right, now we have to fix it up. There we go. So this is what I want you to see. Annual is 1, semi-annual is 2, and that just means twice a year, by the way. The word semi-annual means twice a year. Quarterly means 4 times a year. Monthly means 12 times a year, of course, and daily will be 365. Even during a leap year, it's always 365. All right, so now we're ready for this scary formula. Okay, I think I've prepared you as well as I can for it. The only thing that really is a problem with it is that you have to be extra careful with the parentheses. All right, here we go. I've stalled long enough. Now you're going to see this thing. And when you look at it, you might say, it's kind of involved, but it's not that bad. Oh, all right, hold on. I'm trying to save the file and it's taking forever. There we go. Ta-da! After all that buildup, this is the formula that I've been alluding to all morning. That's the formula that we'll use instead of the simpler version we had before to calculate the future value of a sum. This one is very helpful because now, remember before, when we had 4 interest payments per year, we had to use the other formula 4 times. Not here. This formula will get us, no matter how many times a year the interest is compounded, we can use this formula to get our answer. So, but in exchange for that, the formula is a little bit messier. But I think you'll agree when you do it a few times that this is the way to go. It's a little messier, but we only have to use it once, no matter how often the interest is compounded. Okay. All right. So when you're ready, we're going to look at what we're actually going to do is revisit the examples we had earlier, but we're going to use this formula instead of going through it step by step like we did before. All right. So here's what I mean. So remember, we put $1,000 in the bank for 1 year when the interest rate was 4%. And we want to know the future value of that sum based on the following assumptions. And remember, we did 3 of them: annual, semi-annual, and quarterly compounding. Now, in this case, we already know in advance what the answers are. All right. Remember, the first one is 1,040. The second one is 1,040.40. And the third one is 1,040.604. But we want to prove it with this new formula. All right. Are we ready? Yes, we are. Okay, good. So in the first case, now that's the formula. Those are the numbers we have. N equals 1. So we plug in all the numbers. And if you notice, this is a special, an especially simple case because it reduces this exponent is just 1. 1 times 1 is, of course, 1. And 0.04 over 1 is just 0.04. So basically, this whole expression on the right is nothing but 1.04. And when you multiply that out, you get 1040, which is exactly what we got with the simpler version of this formula. Remember, A equals P1 plus RT. This is for compound interest. All right, so that was a breeze. What about the second case where we had semi-annual compounding? How could we do that with a single formula? Let's find out. The only thing you're changing is n. The rest stays exactly the same. So just keep that in mind, but you have to be careful. And in fact, in each case, I've shown you 2 alternative ways of getting to this information on your calculator. You can pick the one you want. All right. So n equals 2. Now here the n becomes 2. So you basically have, when you come right down to it, all of this is nothing but 1.02 squared. Now, if you look at the first approach that I've taken here, what I've done is I've taken the 1.02 squared and multiply it by 1,000. And if you notice, it avoids the need for any parentheses. If you still want to go from left to right, that's fine, but you do have to use the parentheses. So you may decide for yourself which of these 2 approaches you are comfortable with, and then probably stick with it all the time. So what often happens in these cases is you might be better off doing the more complicated piece first. Like here, for example, obviously 1.02 squared is the most complicated part. When you're done, whatever you get can be simply multiplied by 1,000 to come up with the final result. Or you can go from left to right in the traditional way, but just be aware that that requires parentheses. As long as you can get the answer one way or the other, that's fine. Okay. So I hope everybody got this. And you see, as we expected, the answer is $1,040.40. This is exactly what we got before when we did this the long way. Okay. So, and when you're ready, when you're caught up, we're gonna do the same thing for quarterly, where the only change is that n equals 4. And then again, you already know in advance what the answer is, but why don't we go through the formality of proving it with this formula? So if you're ready, try this with n equals 4, and let's see what you get. All right, here we go. So yes, it worked out exactly the same. Now keep in mind, when you plug all these numbers into your formula, it reduces to 1.01 to the 4th power. Okay. And so then you can choose one of these 2 alternative approaches and you'll get 1040.604. So really the big trick here is to simplify whenever possible. If you notice, we're not trying to do the formula like it is written. We're trying to reduce each term to the simplest possible form. So for example, that's clearly 1.01. and the exponent is 4. So you're implicitly simplifying everything first, and then you're using your calculator. Now, for everyone who's already done, this is the morning challenge for you. What I would like you to do is now see what happens. We haven't done this one yet. See what happens if the compounding frequency is monthly or n equals 12. All right, so what I want you to do is keep this in front of you, plug in 12 for this formula, and see what you wind up with. All right, so I'll give you a few minutes to take care of that. Oh, somebody's got it. My God, that was fast. Oh, Wi-Fi is crapping out on people. I think it's windy out. That's why this keeps happening. All right, if your Wi-Fi is not working, you can watch the video if you need to, which is found on my, as you know, my YouTube page. So yeah, I mean, I know this happens. I know that Wi-Fi can be very erratic. So, but thanks for letting me know. Oh, what else do we have here? Trusty old technology. That's right. Remember, the rule of thumb is that it always lets you down at the worst possible moment. Okay. Yes, trusty, trusty technology. All right. So does anyone have the future value ready for n equals 12? Just let me know. I'll wait as long as it takes. Here's a hint. It's higher than the number you see in front of you. Okay. So in other words, remember, it keeps increasing. The question is how much? Hmm. Well, I'll tell you what. Let me show you the answer. It turns out to be $1,040.74. So it did jump up another 14 cents roughly compared to quarterly compounding. This one is a little trickier because the ratio of 0.04 over 12 is not an even value. So you can round it a little bit. Just try not to over round it. We can do this because the interest would have been rounded to dollars and cents anyway. So why don't you try to keep it at, let's say, 6 places and see if you don't come up with 1,040.74. All right, is everyone pretty much done with this? All right, well, I'll tell you what, this is where I left off with the other class. And I told them, and I'm telling you, I'll tell you the same thing. I think something like this, we really do need a lot of practice. So what we'll do next time is we'll start out, I'll make up some new examples that we can work on together in the class. And when everybody is satisfied that they can do this on their calculator, then we can carry on with what follows. All right, but right now, it's the important thing is to be able to do this formula properly. So I'll make up some new numbers, and then we can try our hand at doing these correctly. And so I'm sure that after you do enough of these, you'll be really good at it. But in the beginning, it is kind of a scary process. Okay, so don't forget that some of you still haven't done your midterms yet. You can have them in by midnight tonight. Eastern time, of course. I assume you're all on the East Coast, but you never know. Some people might be living elsewhere. So I'm thinking midnight Eastern time tonight, you can have it in. I don't know when they're going to get corrected. That's a different question. Most likely they'll have to wait till the weekend. Yeah, I know. It's very disappointing, but that's okay. They'll get done eventually. So in the meantime, I guess we'll stop right here. And we're going to carry on next time with more practice with this amazing formula, the future value of a sum with compound interest. All right. So I think we'll stop here, and I'll see you all on Thursday.
Bye.
All right. See you later.
Bye, thank you.
Thank
Bye.
you. See you Thursday.
See you later.